Hello, my name is Michael Irwin, and I'm coming to you from my basement in Blacksburg, Virginia. I'm coming from Virginia Tech as well, and in this session, we're going to be talking about securing our clusters, or specifically our Kubernetes clusters, with Gatekeeper and OPA, and just maybe a little bit of information about myself, so you know who I am and whatnot. I've been working at Virginia Tech full time. I'm actually hitting my 10-year mark like right now, and I've worn a lot of different hats. I started as a student developer before 2011, and then when I graduated from my undergrad, rolled in full time and started doing some development, and I've done a lot of different things since then. But I found that both through my studies with my undergrad and my master's, that my passion is kind of in user experience, but not in the like end user building user interfaces and that kind of stuff, but more of how do we use computing to smooth out our processes to respond to user needs faster. And so like the whole DevOps space, I'm just totally into it because that's something I really enjoy doing. I am an adjunct faculty instructor in the CS department. I've been teaching about 6 years on and off, and it's been a lot of fun. I'm big in community involvement and development of communities. Here at Virginia Tech, we've got a developer community we call DevCom, and that's been a lot of fun. And I'm recognized in a couple of different areas as well in the industry. I have an awesome wife and 5 kiddos. Hopefully, none of them will run behind me as I'm recording this. And they range from about 8.5, almost 9, to 7 months. And first 4 are girls, and the last one's a boy. So we're there's always something fun going on here at home. And this picture that I have here, it was kind of just a fun thing. DockerCon 2019, my talk was selected to be replayed on replay day, and they don't record that one, so I just decided, hey, let's wear an inflatable dino suit. So quite often people are sending me images or pictures or news reports or whatever if they see inflatable dino suits, because I just think it's hilarious and it's fun. So anyways, enough about me. So the way that I'm going to do this talk is I'm going to first start off with talking about the built-in mechanisms with Kubernetes to do RBAC and why it's not quite good enough for what we need. And I guess I should describe a little bit of what it is that I'm working on and building. And my role right now, I'm helping lead an effort to create what we're calling a common application platform, which right now is being implemented with a multi-tenant Kubernetes cluster. And the idea is to be able to let teams just deploy apps without thinking about the infrastructure or really anything else around it. And these are teams that are typically not going to have cloud engineers or need a lot of the extra stuff that comes with cloud. They're just wanting to run an app. And so we want to make that as easy as possible. But we also have a lot of considerations of how do we make sure that Team A doesn't step on Team B's toes and whatnot. So we're going to talk a lot about those problems today and the mechanisms that we're leveraging to provide those safety nets between teams so they don't mess with each other. So first off, Kubernetes mechanisms. The built-in RBAC mechanisms, and I recognize some of you may know this, some of you may not, and that's fine. In Kubernetes, we have a concept called namespaces that allows you to basically carve up the cluster into smaller virtual clusters, and that's the term that they use as well in their documentation, and allows me to say, okay, Team A, you're in namespace A, and you can't do anything outside of your namespace. You don't even, in fact, you may not even know that namespace B even exists. Okay. The RBAC mechanisms then allow me to control what sorts of things they can do. They can create and update and delete certain objects, but not other objects and whatnot. Kubernetes itself has no mechanisms for authentication. If you think about the number of ways to authenticate between OIDC and OAuth and SAML and CAS and LDAP and user databases and just there's so many different ways. They said, we're not going to be in that game. Good luck. You figure it out. Here's mechanisms that you can use to provide the details once a person's authenticated, and then we'll do authorization. We're using Dex for a lot of that, and if anybody wants to dive more into that, let us know. We'll be happy to talk about how that's all wired together. But once a user's authenticated, Kubernetes does have very rich support for authorization of what are they allowed to do within the cluster. And the way that that's done is by using a combination of roles and role bindings. Now, roles are are the definition of the policies. You can create, update, and delete this kind of object. And we'll see an example of that on the next slide here. The difference between a role and a cluster role is the level of accessibility and scope of visibility that role has. If I create a role is within a specific namespace, and I say, okay, I'm going to create a role maybe for an application, and this app has certain rights and permissions. But if I want that role to be accessible for multiple namespaces, I can't do that with a role. I need to create a cluster role. And a cluster role lets that set of permissions be defined across the entire cluster. So as an example, we define a cluster role that says, this is the definition of a platform tenant, and these are the things a platform tenant can do, and we define it once. Then either using role bindings or cluster role bindings, we can decide are they going to have those permissions across the entire cluster or just within a specific namespace. So a role binding will grant the rights for a role or a cluster role for a specific namespace, while a cluster role binding will grant those permissions across the entire cluster. So again, we use a cluster role to define a tenant, but then a role binding to say, all right, you've got these tenant permissions within a specific namespace. And that way our tenants are consistent, that there's no varying degrees of permission. Okay. Here's an example. Let me grab the laser pointer. All right. So with this cluster role named pod reader, anybody that has this will be able to get, watch, and list pods. On the right here, I have a role binding. And so again, a role binding is going to be attached to a specific namespace. In this case, the example app namespace. I reference the cluster role. And so any users that are in the group OIDC platform example admins will have the ability to get, watch, and list pods in the example app namespace. Okay. So again, this is how it works. Now, again, if you look at this, okay, I can get pretty granular and say you can update these types of objects, but not those type of objects and everything. But that's not quite granular enough for what we need. And the reason is because just because you can create something doesn't mean that you should be able to create all configurations of that thing. One example is actually the second bullet point at the bottom. So if I can create services to be able to expose my application on the network, there are certain types of services I want to support, but I don't want to allow our tenants to be able to just create load balancer services. And so how do I do that? If RBAC is just saying you can create a service, now I'm wanting to tweak this specific configuration, validate specific keys. And I can't quite do that with just roles and role bindings. If I want to make sure that my cluster always has capacity, how do I make sure that everybody's defining resource limits and requests so that I know if I have enough capacity in my cluster? Again, if I'm just granting the ability to create pods, well, now I'm wanting to provide extra validations in that process. And this picture goes along with it pretty well because, the RBAC mechanisms give me this road and this security gate here, but there are so many ways around it. Another example that we run into, and I'll actually use this as an example, is, Team A, we want to let them create their ingress objects to define their traffic, their HTTP. So, request to this domain goes to this service versus that service, and they can control that. But I don't want Team A to be able to potentially take Team B's domains. If they change their ingress to point to Team B, now they're intercepting their traffic, and that's not something we want. So how do we, again, let them create, update, delete their ingress objects, but put policy around the values that are available that they can use? Okay, and we'll actually look at that one specifically. So the way that Kubernetes supports this is by including extension points within the API request process. And the API request process looks something like this. A request comes into an API HTTP handler. It's authenticated, authorized, cool. Then there's a set of mutating emission controllers that what they do is the control plane sends the request to configured controllers to say, do you want to make any changes to this object? Examples might be to add standardized labels to it or inject additional configuration, whatever. There's lots of examples of mutating emission controllers. Once all these run, and these run in serial, so one after the other, then object schema validation is performed just to make sure that any mutations still keep it valid. Then validating mission controllers are triggered, and these will look at the object and find out, should this be accepted? So it's valid schema-wise, but should this be accepted? And we'll see some examples of built-in ones in just a second, and then how we can extend that. If it should be accepted and persisted, then it's actually persisted etcd. It publishes the events. Other things can respond to it. Deployments are made, etc. So this is the process. Kubernetes itself uses this process to do all of its own validations and extend itself over time. Some of the built-in ones, this first one, namespace exists. So if I try to create a pod in a namespace that doesn't exist, well, it's this submission controller that says, hey, that's not a known namespace. Burnt, rejected. Resource quota, if you're using resource quota as a namespace to say, hey, this namespace only has 2 CPU and 4 gig of RAM, if my pods now say I want 3 CPU and 6 gig of RAM or whatever, the resource quota mission controller will deny that. And again, so these are looking at state in the cluster to determine, should this thing be persisted? And there's lots of other ones. In fact, there's 17 enabled by default on new clusters, and there's a whole list of others that you can enable, many of which are deprecated and not really used anymore. But again, Kubernetes itself packages a lot of these in. So the question is, how can we plug in our own emission controllers if we want to extend this and maybe add our own policies or whatnot? Of course, we can write our own, but then we're going to have to update feature gates and all this other kind of stuff, and that gets really complicated. So what they decided was, well, we're going to have one of these controllers that's basically, it receives the request and then it's going to collaborate with other services through webhooks. And then that provides an extension mechanism so that you're not having to go and update all the API server flags and all that stuff. So the way this works is the webhook controller will send a request to a service and then expect a response. An important thing to note here is once you start doing this, those services are part of your control plane. And so, I said control plan. Oh, well, control plane. And so you want to be careful about that. One, they need to respond quickly because it's going to slow down any potential updates to the cluster. But also, if you ever run into the case in which, one of these always rejects things, then you're never going to be able to make changes to your cluster. So you really want to be careful in the sorts of things that you plug in here. All of the services that the webhook will collaborate with are required to use HTTPS, and if you use Cert Manager in your cluster, that makes it super easy. You can use your own self-signed and internal CA if you want, or whatever. The way that you define a webhook is using a validating webhook configuration object. An example looks like this. So in this example, webhook configuration, what I'm doing is I'm creating a webhook named podpolicy.example.com. In fact, I just copy and pasted this from their documentation site. Annotation, I'm going to inject the CA bundle from this place. And so Cert Manager, in this case, is actually acting as a mutating emission controller that will see this annotation. And when I define the object, we'll inject the CA bundle, we'll mutate it into this spot here. And I don't have to have it commented. It knows where to put it. I just have it here for documentation. So I'm going to create a webhook. Here's the name. Here's the review versions that it's going to get. Client config. Whenever an object comes in that needs to be reviewed, it's going to send the request to this service within this namespace. And that's pretty much it. And so at this point, requests will start going to it. And that's awesome. What do these requests look like? Like this. The requests are pretty detailed. They contain a random UID for each request, kind, the resource, the name, the namespace, the user info, the object itself. The old object will be there if I'm doing an edit, so I can compute any diffs between the objects, etc. So it gives me a lot of information. And then it's up to the service to look at it and figure out, well, do I accept this or not? The response is going to be a JSON object that looks something like this. Allowed true if it's good. Allowed false, and then I can provide an extra status code of 403 and a message of, you cannot do this because it's Friday and your name starts with an A. Sure, I know it's a pretty contrived example here, but you can make policies about anything. If you really wanted to make it so you don't deploy on Friday, you can make a policy that prevents you from making changes on Fridays if you really wanted to. Now, the question is, all right, defining your own web server and doing these interactions and everything can be pretty complicated. You want them to go super fast. You want to test them. You want, it's part of the control plane. So OPA and Gatekeeper provide a much easier way to do that. If you're not familiar with OPA, OPA stands for Open Policy Agent, and it's quoting from their marketing page, policy-based control for cloud-native environments. And theoretically, anyways, OPA is being used in lots of different places, not just in Kubernetes, but maybe even like service meshes, or I've seen and heard of some REST APIs that will let you define the rules for who can make requests to various endpoints using OPA. The policies are written in a language called Rego, which we'll see in just a minute. It looks a little funky and it takes a little while to wrap your head around, but it's super fast, and it makes this kind of policy engine, the faster you can make it, the better. Gatekeeper then is a wrapper around OPA and the policy engine. So again, OPA at the end of the day is here's policies, evaluate true, false kind of thing. And then Gatekeeper is a wrapper around the engine so that you can deploy it in Kubernetes and use it as a webhook admission controller. And then it provides mechanisms for us to define our policies rather than files on the file system. We can use objects in Kubernetes using the CRDs and define our policies dynamically and create objects and go from there. And we'll see examples of that in a minute. So again, OPA is the underlying policy engine, and then Gatekeeper is a wrapper around that to be used in a Kubernetes-based environment. Okay, so what's an example OPA policy look like? Well, here's an example here in which what I'm doing is creating a policy that will deny any container images that aren't from my custom registry. Okay, and as Rego's marketing page says, it allows authors to focus on what queries should return rather than how queries should be executed. So you're not going to see any complicated for loops or that kind of stuff. And the way to read these is more or less like truth statements. And every statement is going to evaluate to a true or false. And if it's true, it'll continue execution. Once it hits the first false, it'll stop the execution of this block and go forth. Now, assignments are always going to be truthy, but so let's read this first one together. So the input request, and the input is the input coming from the request here. So this is the input object here. All right. So the input request kind is pod. So this will evaluate to a true or false. If this policy were being evaluated against an ingress object, this would be false and it would stop execution. Cool. So if I've got a pod, all right, let's get the request object, go into its spec, pull all the containers. So this is a kind of a placeholder. It's going to iterate through all the array there and grab all the images and store all the images into a set. So image technically here is a set of all the images in the container of all the containers. If any of them don't start with myregistry.com/, again, evaluate to true or false, then we're going to set the message to say, hey, this image comes from an untrusted registry. Again, a kind of contrived example here, but if you wanted to say, hey, all my images are going to come from a Harbor instance or Docker Hub or whatever it is that you're using, you can easily make a policy to enforce that. Okay. Now, so the way that Gatekeeper plugs into this is, again, Gatekeeper is going to run as a webhook admission controller. And the way that I can create the policies are using what are called constraint templates. The constraint templates themselves aren't the actual policies that will be implemented. They're, again, templates. And we'll see how that works together in just a minute. So once I create a constraint template, then I can create implementations of that object to actually enforce the policy. All right. And hopefully it'll make sense in just a minute. So again, I created a constraint template here, name ingress allowed domain, that will let me say, here are the host names allowed for ingresses. Okay. And once I do that, the OPA actually creates another CRD for me that lets me create ingress allowed domain objects with various parameters on them to parameterize and say what are the host names that are allowed. Now I know this may be a little confusing, so here's an example that hopefully helps it make sense a little bit. So I'm going to create a constraint template, and I'm going to name it ingress allowed domain. And in this, anytime I define an ingress allowed domain object, I need to give it an array of strings that's called domains. Okay. Now, once I do this, it's going to run this rego policy. And in this case, I'm inlining it. When we actually do this in real situations, we use a Helm chart, and then the rego file is separate, so we can run tests against it using the OPA CLI. But in this case, I'm just inlining it. So the rego here is going to check the input kind as ingress. Let's grab all the hosts from all the rules in the ingress object. And then input parameters.domains. So the parameters are going to come from the domains that are on the ingress allowed domain. So I'm going to get all the domains, and then I'm basically going to do some matching between them and find out, all right, when I created an ingress allowed domain and an ingress object, are the names matching here? And we do support wildcarding as well too, which is what makes that a little bit more complicated. So here's an example of me actually creating an ingress allowed domain object. What this is saying is I'm going to look in the example app namespace, and we're going to watch all the ingress objects, and the authorized domains are, in this case, app.localhost. So more or less, this namespace has access to this domain or list of domains, and we can wildcard it as well. So if I try to create anything outside of this domain, something else.localhost, it should blow up and it should fail. And we'll try that out here in just a minute. Now, how we apply this at scale, and we manage this for all of our tenants, is what we have what we call the landlord Helm chart. And the landlord Helm chart, again, kind of going to apartments and renting and tenants and landlords and all this stuff. We just kind of kept the terminology there. It ensures that all the tenants are configured in a similar fashion. And it provides a single place for us to define the tenant config. And we actually deploy this using Helm release via Flux. If anybody wants to talk more GitOps or whatnot, we'd love to. We're doing a migration from V1 to V2 of Flux, and it's awesome. But anyways, we can definitely talk about that. And then we have separate values files for our non-prod versus prod clusters. We pretty much put all of our tenant workloads on our prod cluster, even their feature branches and their staging environments and all that stuff. And our development clusters are really for us to sandbox and test stuff out with, but we also dog food our own processes here. So many of our own services we treat as our own tenants as well. So anyway, this is an example of what it might look like. Each tenant will get their own namespace, their own RBAC setup, their own Flux configuration, placement constraint mutation. So actually, as an example, the sample tenant B, we're setting affinity objects on it. So, or what this will do is mutate every pod that gets created to make sure that pod will only ever go on a node that has a labeled node type of spot. So maybe this is for a workshop or a sandbox or just a group that doesn't really care if it's up all the time or whatever. And so we're just going to put on spot instances all the time. And so we can do those kind of mutations, and they have zero ability to get themselves off of spot instances. So if we've got groups that want to be partitioned from others, we can enforce that with policy and mutation. And then any additional policy configuration, so like our domains, what domains they're allowed to use, etc. So let's actually do a quick demo here. If anybody wants to follow along, here's the source code, and you're welcome to take a look at it afterwards. And I'm going to pull up Visual Studio Code here. In the setup directory, I've got a customization script here that will install both the traffic ingress and gatekeeper, and I'm just doing this against the Kubernetes cluster that comes with Docker Desktop. And so we'll spin this up, get it going, and once it's done that, we're going to apply this constraint template. And this is the same exact one that we were just looking at in the slides for the ingress allowed domain, where I specify the list of domains that are allowed, and then it's just inlining the rego. In case you're wondering too, I have alias kubectl, kubecontrol, however you want to say it, to just K. I know a lot of people do that too, but all right, so let's apply that. And And so now we've got that policy in place. And now I'm going to go actually to my chart directory here. And this is just a subset of our tenant config here. So I'm going to define a tenant named Hello World with this domain. And the rest of this I just kind of kept as examples that you can see, but not all of it's actually being rendered in the template. Like I'm not going to deploy Flux and use that here. So let's go to my chart. I'm going to do a Helm install. And again, normally this is being done in our real clusters through GitOps rather than manual. But if you wanted to run through it, I didn't want to force you to have to do all that other setup too. All right, so what that just did was I should have a namespace now called Hello World, which I do. It was created 11 seconds ago. And what I'm going to do is I'm going to deploy just a simple little app on port 5000. The ingress, though, since we're authorized to use Hello World, let's do something else. I'm just going to make up something else because I can think of random stuff real quick. So we're going to try using something else.localhost and deploy this. Okay. And again, normally our tenants their manifests are being deployed using Flux instead of manual processes like this. But all right, actually, I didn't change the directory yet. Okay. All right, so I'm going to apply this in the Hello World namespace, and I'm going to do these files. And yeah, right now I'm using an old version of Ingress, so just ignore that warning. The service got created, the deployment got created, that's cool. But the ingress failed because it says invalid ingress host something else.localhost. And so it's telling me, hey, that's not a valid domain for me to use. Okay, well, fine. Let's change that back. So let's change it back. I'll apply that. Alrighty, and now if I get the pods in the Hello World, if I can spell it right. So this one ends with XMGNB. And we see, okay, now it's being served by the pod with that name too. So the ingress worked, the routing worked, all that kind of stuff too. So the policy helped protect me here. And again, this is just one example of a policy, but there are many other policies that we could plug in, like for example, the load balancer service, etc. Just as a quick note too, there is a Gatekeeper library that has a lot of commonly used policies, and so feel free to check that out if you don't want to write them all yourself, or if you want to be inspired by some of them. And in fact, we did that for quite a few of ours as well too. So, and with that, I say thanks, and if you've got more questions or want to dive into any of the other topics that I mentioned throughout as well too, feel free to let us know, and we're always happy to share the things that we're doing. Otherwise, hope you have a great rest of your conference, and I'll see you later. Thanks.